Are you actually moving right now, even while sitting completely still? Let's dive into this explainer and absolutely shatter how you perceive the world around you. Welcome to the mystery of motion.
Picture this. You're sitting on a moving bus. To the person right next to you, you're perfectly still. But to someone standing on the sidewalk outside, you are literally zooming past them at highway speeds. So, who's actually right? Well, from a physics standpoint, you both are.
Which brings us to part 1, the illusion of stillness.
To really decode the matrix of the physical world, we first have to agree on a fixed reference point to measure any change in position over time. See, motion absolutely requires a frame of reference. You can't just say something is moving. You always have to ask, moving compared to what? Is it the stationary tree or is it the speeding train?
Moving on to part 2, path versus final position. Now that we know we're actually moving, we have to figure out exactly how we measure the journey itself.
Wait a second. Can an object travel a huge distance but have zero displacement? To solve this little mini-mystery, we need to understand that the physical world tracks our movement in two entirely different ways.
The secret here lies in the difference between two core concepts. Distance is what we call a scalar quantity. It only cares about the total ground you covered, no matter how crazy or winding the route is. But displacement? That is a vector quantity. It strictly cares about the shortest, straight-line path from your starting point to your finish line, and it absolutely requires a direction.
Let's bring this to life. Imagine you travel from an origin point, let's call it point O, all the way out to point A, which is 60 kilometers away. Then, you turn around and walk all the way back to the origin. Your total distance traveled is 120 kilometers, but your displacement? Well, because you ended exactly where you started, your displacement is a perfect 0.
Now, as you travel, your rhythm really matters. If you maintain a steady pace, covering equal distances and equal time intervals, we call that uniform motion. Think of a ceiling fan rotating or the Earth orbiting the sun. But in real life, your pace constantly fluctuates, right? That is non-uniform motion. Just think of a bouncing ball or a car constantly stopping and starting in heavy traffic.
All right, part 3, speed, velocity, and direction. Let's uncover how we actually measure the sheer intensity of all this movement. When a cricket bowler hurls a ball at 143 kilometers per hour, or you see a big 50 on a speed limit sign, we're talking about speed. Speed is simply the rate of change of distance. Basically, it's just how fast you are covering ground. But just like distance, speed has a much more sophisticated sibling, and its name is velocity. Velocity tells you not just how fast you're going, but exactly where you are heading. Because it relies on displacement rather than distance, velocity must always include a specific direction. So, how do we actually calculate this stuff? Well, if you take a 2-hour road trip covering 100 kilometers, your average speed is calculated using a super simple formula. V equals S over T. That's distance divided by time. So 100 kilometers divided by 2 hours gives you a nice average speed of 50 kilometers per hour. Which brings us to part 4, the thrill of acceleration. What actually happens when you slam on the gas pedal of a car or dive down a massive roller coaster? Here is a crazy question for you to think about. Can something accelerate even when its speed stays completely constant? Before we answer that, let's look at what acceleration actually means in the physics universe.
Acceleration is literally the thrill of change. It happens whenever an object's velocity increases, decreases, or even just changes direction over time. The magical formula here is A equals V minus U divided by T. That's your final velocity minus your initial velocity, all divided by the time it took.
Let's plug some real numbers into that formula. Imagine jumping on a racing bike from a dead stop, meaning your initial velocity, your U, is 0. You pedal hard and reach 6 meters per second in exactly 30 seconds. So, 6 minus 0 divided by 30, that gives you an acceleration of 0.2 meters per second squared. Simple, right?
Moving right along to part 5, graphing and calculating motion. Let's take these invisible forces and make them totally visible using graphs and equations. This is where we simplify really complex motion. It's so cool how a car's journey just transforms on a grid. A simple sloping line on a distance time graph instantly reveals the object's speed. And even more amazing, on a velocity time graph, if you calculate the geometric area directly under that line, it magically gives you the total distance the object traveled. You're literally seeing the journey drawn right there on the page.
And to calculate that journey, we use what are basically the cheat codes to the universe, the 3 equations of motion. First, v equals u plus at. Second, s equals ut plus 1/2 at squared. And third, v squared minus u squared equals 2as. By relating velocity, acceleration, distance, and time, these equations literally allow you to predict the exact future of any moving object.
Finally, Part 6, the circular motion mystery. Let's wrap up by solving that lingering mystery about objects moving in circles, like satellites orbiting the Earth.
Imagine you swing a stone tied to a string around your head, and then suddenly you let go. Why does it fly off in a perfectly straight line instead of continuing to curve? Remember that question from earlier?
Well, here is the incredible secret of uniform circular motion. Your speed might be totally constant, but your direction is changing at every single microscopic point along that circle. And remember, because direction is changing, velocity is changing. And a changing velocity means you are constantly accelerating. The string is constantly pulling you into a new path. Once that pull stops, the stone simply obeys physics, following its last given direction straight ahead.
So I leave you with a quick challenge. If a car starts from rest and accelerates uniformly, can you calculate exactly how far it travels? With the tools of displacement, velocity, acceleration, and our 3 magical equations, you now have the power to solve this yourself. I'll leave you with this final thought. Motion isn't just about moving. It's about how we describe change. Because ultimately, understanding physics is about looking at the world around you and realizing that nothing is ever truly sitting still. Everything is relative and everything is in motion. Keep observing, keep calculating, and I'll catch you on the next explainer.